Good afternoon, everyone. Welcome to the physics seminar for today, the 20th of April. And we are pleased to have one of our own students, Mr. Trent English, who I assume you successfully defended your thesis last week.
Yes.
So Master English, welcome. Glad you're here today to give your talk for us on the concept of studying and observing galactic neutrinos in I meant Neptune's atmosphere. And you'll say it better than I will anyway. So anyway, so let's welcome Trent.
Thank you. Oh, yeah. And it looks like everyone can hear me as well. And I don't see Dr. Salama yet, but that should be fine. All right. Right, but the other people at NASA were wanting to listen in on it as well. All right, hello everyone. So my name is Trent English, and so today I'm going to be giving the seminar over the concept study for observing galactic neutrinos in Neptune's atmosphere. So this was what I defended my thesis on just this past Friday, and I've been working on this for at least the past school year so far, and started a little bit into last summer. So overall, let me get that going. So overall, what I'm going to be covering today is 8 different sections, starting with introduction motivation to my research, why ice giants can be used as targets for galactic neutrinos, getting into the simulations that I did with Neptune's atmosphere, the results from the simulations that I got, getting into more of the conceptual side for the detector design, and then some of the future work and refinements that I want to do, especially finishing off this semester and into the summer as well. And then talking about the versatility that this type of detector can hopefully be used for, and then just finishing off with the conclusion. So in the introduction motivation, I'm going to start with where did this begin overall, what motivated the research that I wanted to study, and then a little bit into the gravitational lensing with neutrinos. Now, getting into where did this begin? So starting also with the NuSOL project, so the Neutrino Solar Orbiting Laboratory, which is based here at Wichita State University. From that study of answering the question of what if we go away from the sun, and some of the initial studies that was done from a senior physics project. Now, NuSOL, as I said, is a project based here at Wichita State University. So it's going to be the first space-based neutrino detector that is wanting to study neutrinos that are being generated via fusion in the core of our sun. And so currently we're in NIAC phase 3, which is going to be used to develop a demonstrator mission as a CubeSat that is going to be launched hopefully at the end of the summer of 2024. And after that, for future missions, having a larger craft that is going to be going towards the sun to have an increased flux of these neutrinos as we get closer. And as a show of how much the neutrino flux will increase is, so at 3 solar radii from the sun, we can have an intensity of about 10,000 times that of what we experience here at Earth. And while we are there, and also while we are approaching, we can perform various studies of that, such as off-axial measurements, given that all the measurements we currently have for the solar neutrinos are fixed here at Earth. And so as we are orbiting, but also approaching, we can go off-axis and see how those rates change. Perform neutrino oscillation measurements as we start to approach the sun, and then also possible measurements for upper limit of the neutrino mass. Now, from that study, and even though it's still going on, we also want to answer the question of what if we go away from the sun? So as we go further from the sun, we'll have the flux of solar neutrinos continue to decrease by this 1/r² factor. And then we can also get into some studies of dark matter, which was actually done by a master's student who graduated last spring, Shrey. And we can also start to look at other sources of neutrinos, even though the sun is the brightest source of neutrinos that we can currently measure. The second brightest source is actually the center of the Milky Way galaxy from various processes that occur there. Now, tying into looking at these other sources of neutrinos, so a senior physics project, which was conducted by Lynn, who actually graduated with their master's here last spring. This was done during their undergraduate time here as well. But they were looking at these stellar neutrinos coming from the galactic core, given that there are about 10 million stars within a 1 cubic parsec of the center of the galaxy. And so they were looking at what would be the rate increase of these stellar neutrinos when they are gravitationally focused by our sun. Now, I'll talk more a little bit about gravitational lensing in just a little bit, but at least from Lynn's initial findings, they saw that these stellar neutrinos increased, or the flux of these stellar neutrinos from the galactic core were increased by as much as 800 to 8,000 times that rate of what we measure of solar neutrinos here on Earth. Now, granted, that is out at the focus, which is quite a far distance, especially when Lynn was only considering neutrinos focused outside the sun, so similar to that of light. And then also, Lynn was only looking at the stellar contributions and not all other contributions, such as neutrinos generated via processes near the accretion disk, which would have met them at very high energies. And so they were only looking at this one subtopic and not looking at those higher energy contributions. Now, getting into what motivated at least my research overall is using these neutrinos to actually study and observe the galactic core of the Milky Way, even though that is part of what we're wanting to do in the future, but that is what essentially motivated this project. And then, are there different ways that we can use these gravitationally focused neutrinos to perform other experiments? Now, looking at, actually, to go back at this, so the picture I have here is looking at at least a panorama view of the Milky Way in total, but more in the visible spectrum. And at the center of the bright spot is the galactic core of our Milky Way. And so one of the difficult things with that is we cannot peer through that dust and debris that is currently obscuring our line of sight without using other forms of observation, such as looking in the infrared and the radio spectrum, which then we can start looking through these obscurities and get a better view of what is at the center of our galaxy. Now, the figure on the left is looking at the galactic core in more of the infrared spectrum. And so we can see that we have Sagittarius A in the center, which is actually the supermassive black hole at the center of our galaxy. And then we have a few stars that are orbiting Sagittarius A. Now, the observations of the orbital periods of the stars going around Sagittarius A is helped to what concluded that Sagittarius A had to be a supermassive black hole, given that some of the orbital periods range from as short as 13 years to a few thousand years. And from that, they were able to determine that Sagittarius A had to be a supermassive black hole because the gravitational attraction showed that the mass of Sagittarius A was about 4.15 million solar masses. Now, is there a way that we can start looking more into Sagittarius A itself? And if we look on the image on the right, we are now looking in the radio spectrum, which we are seeing this superheated gas that is currently encircling Sagittarius A, but we do not see anything that at least resembles what we conceptually see as a black hole, like the one that was published back in 2019. And so, but this is not an image of the black hole in the center of our galaxy, but actually the center of M87, which is about 55 million light years from Earth. Now, why have we been able to get an image of this black hole, but not the one in the center of our galaxy? And part of that is the black hole from the center of M87 is actually 1,500 times more massive than Sagittarius A. And so this accounts for the us being able to resolve the overall black hole from the massive size, but also having a collaboration of telescopes being able to observe this one spot. But so we don't see that same feature in the previous image. And is there a way that we can start to at least probe further instead of using either infrared or radio? And so this led to, can we use other particles instead of that of photons? Now, any of the charged particles emitted from the galactic center are going to be deflected from the magnetic fields that are surrounding them. And so even if we were to get any kind of particles here at Earth, they are not coming directly from the center of the galaxy to us. They're going to be deflected and have some strange path before they get to us. Now, we can possibly use these ultra high energy neutrinos, given that they're not charged. So they are going to go between us or between the center of the galaxy and us, being essentially unaffected, and they can go through matter very easily. Now, looking at least some of the contributions of the different fluxes of neutrinos. So we see here on the graph that we have the solar neutrinos, which are essentially the most prominent ones that we can measure. But the ones that we are more specifically looking at are these neutrinos from the AGN, which is the active galactic nucleus. And now, even though our galactic center is a little bit calmer than some of that of other galaxies, we can still use these energy ranges and to start looking at what we would want to see when we start doing some of the simulations. And then also, even though the flux of these neutrinos are very low in respect to some of the other contributions, we can find ways to essentially enhance the flux signal, but also trying to get rid of that solar neutrino background. Now, the way we can do that is using the concept of gravitational lensing, which was first proposed by Einstein back in 1912, and later he fully went into detail with it in about 1930s. And so the concept of it is that any kind of massive object is going to cause light to be deflected from its original path. And so things such as stars, galaxies, and black holes will cause these deflections to occur. And so if we can do that, why have we not done it with our own sun? Now, so the gravitational focus of our sun is an astonishing 550 astronomical units away. And so at least to give an idea of how far we would have to go, I put a example distance that Voyager 1's been going for more than 44 years, and it's only been able to make it 156 AU. So that is something that we would not probably be able to accomplish with larger telescopes in the near future, but we can still use this concept of gravitational lensing, but using neutrinos instead. Now, for the lines coming on the outside of the sun, such as these three lines occurring, that is what we would typically expect for photons, because they will not be able to pass through the interior of the sun without interacting at all. But this line that's going through the center is going to be more of what we would expect with neutrinos, because they can actually pass through matter fairly easily. But one thing that we also have to account for is the energy and how close does it get to the center, because then we start having a chance of these neutrinos interacting with the material, which I'll discuss a little bit more about that in a little bit. And then kind of going over some of the features with gravitational lensing and neutrinos. So as I mentioned, they can pass through the interior of the sun. Because they can do that, they'll have a greater deflection. And with that deflection, it'll have an increased or a lowered focus to being around 22 AU, which is much more reasonable than that of 550 AU with photons. Now, again, we have this increased light collection power using neutrinos, which is on the order of about 10 to the 13th, whereas for typical light, it's on the order of about 10 to the 11th. And that's just because since the neutrinos can pass through the interior, we have more area that we can pass through, and so we have an increased collection power. And then, as I mentioned, with the transmission of these neutrinos, it depends both on the energy and how close it gets to the center. And so we might not see that exact same flux spectrum that I showed previously, but we can start to account for, as they pass through, how many of them are able to be able to measure at the ice giants like we want to study. So getting into the next little section is the ice giants as targets for these galactic neutrinos. I'm going to talk about at least some of the examples of neutrino detectors that we have here on Earth, benefits of using the ice giants for these galactic neutrinos, and also when do these planets align, given that they're orbiting, and so they will come into the focus every so often. So I give essentially 5 main examples of neutrino detectors, ones that are more well known than some of the other ones. And so Super K, which is a neutrino detector that uses a 50 kiloton vat of water and is lined with thousands of photomultiplier tubes to measure these solar neutrinos interacting with the water, and they can measure the shrink-off radiation created from. Oh, sorry, let me mute someone. So Super K measures the shrink-off radiation of these neutrino interactions in the water, and because of the amount of photomultiplier tubes that they have surrounding their detector, they're able to have increased resolution to find out where these interactions occurred, but also where do they come from, at least source-wise. IceCube does a similar idea in measuring the shrink-off radiation that occurs from these neutrino interactions, but uses the natural media of the ice in the South Pole instead. And the overall area of IceCube actually encompasses 1 cubic kilometer, given that they wanted to increase the space as much as they could, But since they're using the ice on the South Pole, they're not having to build nearly as much. They just have to excavate out some of the ice to put their photomultiplier tubes in and measure the shrink-off radiation. Now, ANITA and ARA are very similar to that of IceCube, given that they use the natural media of ice for these neutrino interactions, but they use a different process called the Askaryan effect, which is very similar to that of shrink-off radiation, but instead of visible light that's produced, it produces a burst of radio waves. And so ARA is actually adjacent to IceCube, and so it measures the radiation or the radio bursts that are created from these interactions. And they're also doing collaborations to find out if there's any correlation between the detections they get in IceCube and ARA at the same time. And then ANITA is actually a high altitude balloon that will go up and measure these radio bursts that come up from the ice at the same time. And then to give an example, so we have NuSol, which is going to be the first space-based neutrino detector. But instead of measuring shrink-off radiation, it's going to be using a scintillating material, which is our GAG crystal. Now, the benefit of using this crystal is the fact that it has gallium within the crystalline structure. And so it uses a characteristic double pulse from these neutrino interactions to make sure that we have a neutrino event that occurred within our volume. And to give at least an example of another benefit with NuSol is, so since this will be a space-based detector, we can't send something that is very large into space, given how much it will cost and just the overall mass. And so by sending a smaller detector to the sun, a 100 kilogram volume at 3 solar radii will actually be the equivalent of a 1 kiloton detector here on Earth. And so we have some of the benefits of that, but at least these are some of the examples, and we can use some of the concepts from these type of detectors for the study that I wanted to do. Now looking into this image right here, which is actually produced by SuperK, and this is looking at the solar neutrino interactions within their detector. And they actually reconstructed an image of the sun from these neutrino interactions based off of the trajectory of the incoming neutrinos, and then being able to reconstruct an image. And one of the interesting features is that most, or at least half the data was when SuperK was on the dark side of the planet. So we had these neutrinos coming or passing through the planet and being detected in SuperK and being able to reconstruct an image. But we can kind of use the same concept later when we want to image the galactic core, doing this pixel image. Now, getting into a little bit of the benefits of using the ice giants for these galactic neutrinos. So both Uranus and Neptune are near the focus. So Uranus sits about 19 AU, while Neptune is at 30. Now, even though that 22 AU is the closest focus, that doesn't mean that we won't have increased flux for that of Uranus. And then Neptune, it is in an optimal spot, given that it's a little bit past the 22 AU, but we can have other focuses that pass through the planet as well. So we have a very large increase of flux that can go through both of these planets. Again, there are natural targets, like I discussed with that of IceCube, ANITA, and ARA, so we don't have to take large detectors out there, and we can actually take something smaller, similar to that of like a camera or a telescope, to be able to look at these interactions within the atmospheres. And then, as always, we can perform other measurements while we are there as well. So getting into some of the neutrino interactions. So the basic scheme for it is that we have a neutrino of a specific flavor come in, interact with a neutron, and then we'll have a converted lepton and a proton that will continue on in similar direction of that of the incoming neutrino. And so one of the things that we want to look at is, especially with the lepton, it'll be able to continue on further, and we want to look at the shrink-off radiation and possibly scintillation and delayed fluorescence as this lepton is passing through the atmosphere. And so how can we detect that? Either using camera, and then what kind of signals would we be able to get? And I've mentioned before that as we increase the energy of these neutrinos, that they'll have a higher chance of interacting with material. And so showing the cross-section of a neutrino interacting with the nucleon at these high energies, we can see that it continues to just continuously increase, meaning that we have a higher chance for a neutrino to interact with the nucleon. So even though that Neptune and Uranus are not made of a very dense target, at least for some of the outer atmosphere, that is still okay when the apparent cross-section continues to increase with energy. And I mentioned with also when do these planets align, because they're going to be orbiting and passing through the focus. So for Uranus, we actually pass through the focus around 2032, 2033, while Neptune passes through about 2065 to 2067. So even though Uranus is about 10 years out, we would not be able to get that one done, given that we would have to make a detector and send it out there very quickly. And then even if we sent it, we would not be able to stop once we got there. But Neptune is still within the foreseeable future, since that is about 40 years out from now. And if we were to miss these opportunities, then researchers in the future would have to wait the full duration of the orbit until they realigned. Now getting into some of the simulations that was done with specifically Neptune's atmosphere, given that the composition between the two are very similar. And so just looking at the interactions of what we would expect in Neptune's atmosphere. So I'm going to be discussing some of the computational tools that I had to use, the atmosphere and detector construction within the simulation, approximations that I had to use for the atmosphere, given that we have not been to Neptune since the Voyager mission. So there are a lot of pieces of information that we have to approximate. And then overall, how do we run the simulations? So with computational tools that I use, so there are three main things, and that is GEONT4, Root, which is, again, a data analysis framework, and then the Bioshock High Performance Computing Cluster here at Wichita State. So GEONT4 and Root are both maintained by CERN, and Root works very conjointly with GEONT4, but can be used separate for other data analysis. But with GEONT4, one of the main things is that it'll facilitate the propagation of particles through material. So, and any of the interactions that we are wanting to study. But one of the things is it's very modular in what kind of physics list we want to load, geometries, and the property of the material. So if there are things that you don't specify with it, things won't turn on, or certain processes won't essentially happen while these particles are passing through. And so we want to try to be accurate as possible while we are making these simulations. Now, Root, I said it works conjointly with GEONT4, so any of the data that we are creating with GEONT will automatically come out, or we can set it to be a .root file, so we can then read it into Root and manipulate the data into forms of histograms or any other way that we want to represent it as well. And so all the plots that I made today are all within this Root software. And then Bioshock is the high performance computing cluster. So various softwares that you can use for different areas of research. But one of the main things is we were able to get GEONT installed on that this past spring, or this past fall. And some of the benefits to that is the amount of cores that it has. And then also some of the high memory cores have up to 1.5 terabytes of RAM. And this, I had to use that given that I had a memory leak in my code that would on occasion reach about 500, 600 gigabytes of RAM. Which I recently was able to find where that leak came from. And so a lot of the data that I present, I will be going back through this summer to take more data of the interactions that would occur. Now within GEONT, so we cannot simulate the entire atmosphere, given that that would be a large volume that the simulation is going to try to create. So I went through with just a chunk of the atmosphere, essentially near the surface, what we would expect from some of the interactions that would be close to that of our detector that is orbiting. So about 100 by 100 by 100 kilometer volume is created. And then especially with GEONT, we have to make sure that we define the material using data that we know. So using the volume composition with about 80% molecular hydrogen, 19% helium, and 1% methane. And since GEONT4 does not understand volume fractions, I had to convert those over to make sure that we had the correct mass fractions instead. Now, some other things that we can define that definitely help with the energy deposition is the density, or the state of matter of the material. So making sure that we define it as being a gas, the temperature, pressure, and density as well, just so we can be accurate to the values that especially NASA has on files. And all of those values do help to create an accurate representation for the energy deposition as the particle passes through. Now, the detector, the overall material does not matter. And so overall, we just want to make sure that the shape corresponds to something that we would use either for a camera or that of a telescope. So giving it a cylindrical shape with end caps pointing towards the atmosphere. And then as these photons leave the atmosphere, we are essentially counting the number of photons that interacted or that at least passed through that logical volume that I created. Now, as I mentioned, there's approximations that had to be made, and especially because the optical physics within GEONT 4 are not something that is automatically turned on. So that is things that if we were looking for any kind of scintillation or shrink-off radiation, we have to make sure that we define certain properties. So some of the stuff that I had to go through and approximate was the index of refraction of the material, the attenuation length, and then scintillation properties, just so we can have results that would be accurate to some of the stuff that we want to study. So getting into the index of refraction, so because the composition of Neptune is primarily hydrogen, I went with the assumption that since it is mainly hydrogen, then we can use the index of refraction of hydrogen at various wavelengths and plug that into GEONT to be at least as a good approximation until we can do future studies. And since it is mostly that one composite or that one material, then okay, this should be fine for at least some of the initial studies that we want to do. Now, lambda is the wavelength of the light that is interacting with the material in units of micrometers, and n is the index of refraction at each of those different wavelengths. Now, getting into the attenuation length, so that's just the distance that the intensity has dropped by a factor of 1/e. Now, if we do not define that at all, GEONT will automatically set it to infinity, which is not accurate, especially when we are wanting to do these large volumes. And so going through using the opacity of the material to find at least a reasonable attenuation length, especially, again, since most of these values are not studied already. But some groups have actually gone through with calculations given the metallicity of the star in that region, and then looking at the various pressures and densities and temperatures of some of these giant planets that would be in those certain regions. And from their calculations and using the properties of Neptune, I was able to find a Rosler mean opacity that at least was in the region for pressure, density, and the corresponding metallicity of our sun, to then take that value and get an attenuation length out of it. Now, the Rosler mean opacity that I found was about 9.989 times 10 to the -3rd, and that's in centimeters squared over gram, but had to use the corresponding density of Neptune to then convert that into a reasonable attenuation length, which is about 2,200 meters that these particles would be able to go through before their intensity dropped by 1/e. And then also looking into the scintillation properties, and from some of the studies that I was looking into, not many people have looked into at least hydrogen gas specifically, or this kind of combination of hydrogen, helium, and methane, and what kind of scintillation properties that it has. So what I started using was, as first approximations, is the scintillation properties of our atmosphere instead, which, even though it is comprised of mainly nitrogen, using this as almost a worst case scenario of data that we have on hand. Now, as particles are passing through the atmosphere, it'll create about 4 photons per MeV, which is a very low value in comparison to some of the scintillation materials that we use in the lab, such as plastic scintillators, which have about 10,000 photons per MeV that are created as a particle will pass through it. And since I'm going to be using this 4 photons per MeV, I'm also going to use the spectrum of our atmosphere, which is about 300 to 420 nanometers, and program those values into GEONT, just so as a particle is passing through, we're going to have scintillation and shrink-off radiation both be emitted during those processes. Now, overall running the simulation, so there was a lot of parameters and characteristics that I wanted to study. And since I was doing that, I was able to use a batch file, which I'd gotten from John Folkerts, who is on the NuSol project with me. And so from that batch file, we essentially tell it what parameters we want to loop over and make sure that it updates the corresponding values in our GEONT files. And the values that I was specifically looping over was these different particles, electron, muons, and tauons, given that those are the three flavors that we would expect from these neutrino interactions. And then going through the neutrino flux, so the lowest values being about 10 GeV, and then going up to 10 TeV, given that that's the highest that I could go before things started to bog down with that memory leak that I had. And then also the interaction depth. So where in the atmosphere did it interact at? So 10 to 100 kilometers within. And then trying to see how do those results change at those different interaction depths and what do we measure outside. And then also orbital distance. So either being very right at the surface and then also increasing that distance by 100 kilometers each step until we got to 400 kilometers. Just to have an idea of how do these detections change as we get further from the planet. And then I looked at these runs separately with shrink-off radiation and scintillation respectively, and looking at those total distributions, which I'll show in the results section. So to do that, I created a 100 by 100 kilometer array that would be looking at these total distributions just to understand how the behaviors changed given the different energies, but also the different interaction depths as well. And then when I was wanting to study more of what a reasonable detector would see as it's orbiting, created singular arrays that span the width of the atmosphere, and but with various sizes as well, just to see what kind of size would work best for this kind of concept study that we want to look into. Now, JAN4 does have neutrinos built in, but they're mainly used for conservation of energy and momentum in the form of decays, but they have no interaction properties. So to our first order, we were just taking that these leptons were being fired with the corresponding energy, not worrying about the previous interaction, just that they took all the kinetic energy from the interaction and then propagated through the atmosphere. Now, just as a basic visualization, which it is hard to see the box on the right, given that it is a blue volume, but so on the right, we have the box that I created with Neptune's atmosphere and all the characteristics that I defined for it. And then on the left is this 100 by 100 kilometer array, just to see how that those distributions of scintillation and shrink-off photons changed as we get further and further. Now, going over the results of simulations. So especially for today, I'm only going to be presenting the electron data because there's a lot of different subtopics that I studied. And so I would not have enough time to go through all of them as well, but I show a couple interesting characteristics of the muons and tauons, and then getting into the results that I specifically looked at: total shrink-off hit distribution, scintillation distribution, simulated detector size, and the wavelength. I did also study the timing as well, which I had presented during my defense, but to at least shorten the time today, just so I didn't take too much, I was just going to take that out for at least right now. But these are the overall areas that I was studying. And also given that I had this severe memory leak, I was only able to run one particle at a time. But that's part of the future studies that I want to do, is doing more of these runs as well. So getting into these distributions. So as you can see immediately, right at the surface, we have not too many hits that are incident on the detector, and part of that is because the geometrical shape that I applied, giving this cylinder end caps pointing towards the planet, I had an issue that, especially when we were right at the surface, that a lot of the photons actually pass through the detectors, so there was a little gap right there. But that's something that I'm correcting for some of the future simulations. But then we can see that we get hits for as we get further and further out from these orbits, so 100 kilometers, 200, 300, and 400. And then the majority of what we want to understand with these is, for one, how do the shrink-off ring that's created, how does that change at the different orbits, but also looking at more or less the flux of these photons passing through at least a 1 square kilometer, which that is the bending size. So these squares represented is a 1 by 1 kilometer, and just looking at how many photons do we see for some of these shrink-off rings that pass through. Now, this is for a 10 GeV electron at a depth of about 10 kilometers. And then if we try to go any further to 20 kilometers, we get almost no signal. And then we can start, as we increase the energy even further, we see this more well-defined shrink-off ring starting to appear. And especially for the closer that we get to the planet, we will have a high concentration of these photons passing through, this small region, but as we get further and further, this ring will continue to grow, just given the geometry of the system. And so just looking at how far can these particles interact within the atmosphere and that are still measurable to us, and especially what kind of energies do we need to get these kind of reasonable signals that we would see. And so especially for some of the instances, we have on the order of a few thousand to a couple 100,000 photons passing through these 1 square kilometers. But some interesting areas that we can also see between this 10 and 20 kilometers, that we get almost a more diffusive behavior of these shrink-off rings, given that the electron is slowing down. So the shrink-off ring will actually change in size. And so we have a larger spread that we can start to look at these kind of interactions. So we don't have to be directly at the sides where the ring is mainly created. We can also start to look at more of in the center and see how did the number of hits change. Now, again, these are not ones that we would specifically see, just because this encompasses 100 by 100 kilometers, but just to give us an idea of what the interactions at least create in the atmosphere. And especially this kind of case of we have a 10 TeV electron passing through on the order of about 500,000 photons that are passing through a 1 square kilometer segment. That kind of gives us an idea of, okay, what kind of size of detector would we need to get a reasonable signal out of that? But I start to look at that more in the next section of these different detector sizes and what do they see at the various orbits. Now, this was for the case of the electron. Now, for the muon, one of the interesting things about it is that the muons have a fairly short lifetime, so they will decay after about 2 microseconds. But so this is showing a 100 eV muon at a depth of about 60 kilometers in the atmosphere, so much deeper than the ones I showed for the electron cases. But the interesting portion is if we go another 10 kilometers in the atmosphere, we then see a burst of photons that begin to appear because the muon decayed into an electron near the later portion of the atmosphere. And so we were able to see that, oh, we get something that looks closer to that 100 GeV electron case, but this is when the muons interacting much deeper than that of the same case in the electrons. And then when we start to look at the tauons, especially for some of the low energy cases, is that their lifetime is on the order of a picosecond. And so when they decay, there's chances to create multiple charged particles. And so we can actually see that we have multiple rings that are created, and they are actually very off center from where the initial particle is started, which is at the 0,0 point. And so just trying to see that, okay, with the tauons, especially at the low energies, if we were looking during the orbital transit as we go across, the shrink-off rings are actually presented about 10, 20 kilometers off of where the initial interaction occurred. And then as we increase the energy of that tauon, it'll become more concentric to where the interaction path through the atmosphere was. But we also see that more of these rings are generated given that more energy is given to the tauon. So we have chances to create more of these particles at the same time. And even with this 1 TeV tauon at 10 kilometers, we saw that we still get on the order of about 16,000 photons in a 1 square kilometer segment, but still not as much as that of the electron case too. Now, on the flip side, when we start looking at scintillation, so with scintillation, it's more of an isotropic feature, meaning it's going to have particles emitted in all directions instead of with that of shrink-off, which creates this well-defined cone leaving the atmosphere. And when we start looking at what kind of signals we would see for the scintillation case, given that there is only about 4 photons per MeV, we can start going through and seeing that at the surface, we'd be able to see some areas that get these very high signals, but immediately as we go any further, these kind of signals start to drop off. So even at the case of 10 TeV, where we were getting a couple 100,000 photons in a 1 square kilometer segment, at 10 TeV for that of scintillation, we can have as much as 20 photons on that end. But if we're right at the surface, we can have 1 square kilometer segments that have on the order of about 160,000, but that is very localized. And so if we were to miss that, we wouldn't be able to see it. But especially for the further orbits, we get almost no signals that we'd be able to see with scintillation. Now, I show at least an example of that later when I start looking at these simulated detector sizes. So the way that I did these simulated detector sizes was looking at different sizes, about 1, 2, 5, and 10 meter wide detectors. And as I mentioned, I create this singular array that spans the entire width, and the array size is dependent upon the size of the detector that I was looking at specifically. And so looking at both the same properties that I mentioned previously, and more specifically, the lowest and highest energies, so the 10 GeV and 10 TeV, just to see what the worst and best signals would be for those cases. Now, the binning that is created for these detectors are corresponded to the size of the overall detector I'm looking at. And so each of the bins that are represented are the exact size as well. So as we go through between some of the worst and best case scenarios, we see that for the worst case scenario, for all the orbits, or at least the further orbits, that we get essentially no signals that are incident on our detectors. And then as we start to increase the energy, we start seeing that more of the detectors do have some signal, but they're very minimal and would almost result in no overall detection. But we see that at the surface, even at the 1 meter size detector, that we start seeing this very nice well-defined peak. But that is very localized to at least within about 1,000 meters that we would have to be aligned with that initial trajectory. And then as we start going up with detector size, we start seeing that we can have cases at the surface where we start getting more reasonable detections. But again, at the later orbits that we see almost no reasonable signal that we would have. But once we start getting to the 5 and 10 meter case, we can start seeing more noticeable signals in a lot of the detectors for the further orbits. But we can start seeing these well-defined peaks that start to get wider and wider as we increase the orbital distance. And part of this is because as we saw earlier, there's these very nice well-defined shrink coverings that are emitted from the atmosphere. And so the peaks that at least seeing in these kind of histograms is showing that if we're on either side of the initial trajectory of the particle, that we could see signals in quite a few of our detectors as well. And especially if we are right at the atmosphere and within about a 1 kilometer segment of the initial trajectory, that we start seeing photon hits on the orders of about 10,000 to 100,000 that are incident upon our 10 meter size detector at least. And then looking also at the scintillation, looking at the 10 meter size, because if the 10 meter wouldn't be able to see any of the scintillation hits, then neither would the 1, 2, or 5 meter sizes. So at the lowest energy case, almost none of our detectors got anything. So at the surface, they got on the order of 1 for some of them, but any of the further orbits, it didn't get any signals. And then the 10 TeV case, we actually do start seeing some reasonable signals, like I had mentioned before with the 2D plots. But for any of the further orbits, again, that signal drops to essentially nothing. So if the scintillation of the atmosphere is similar to that of Earth, then we would not be able to detect that to within any reasonable cause. But again, these are only for 1 photon at a time or 1 particle at a time. But as we start running through, just making sure that in any of the cases, do we actually get any signals? That is part of what I'm going to be studying over the summer. Now, another thing I wanted to look at was also the wavelength of these photons that are incident on the detector, because what we typically think with shrink-off radiation is a burst of blue light that occurs, especially when we think of charged particles passing through water and you see a blip of blue light. But for these kind of interactions, what kind of wavelengths are we expected to see? And also I wanted to study, is there any kind of correlation to the wavelength of the light and also the positions where they are hit upon our detector? So looking at just the wavelength itself, it actually creates just this very nice plot that goes very high with the signals around the 300 nanometer mark, and then dropping down to more of the 700 nanometer. So we see that, especially for all the different plots, that the mean is around that 450 nanometer range. And so all of our signals are primarily in this UV to blue portion of the spectrum, while tapering down to the later ends of green and into red. And so when we start to wanting to look into this kind of detector design, which I'll discuss in the next chapter, is we want to, for shrink-off radiation specifically, start looking at these UV and blue detections that are incident upon our detector instead of just the entire spectrum. And then when I start looking into specifically the wavelengths of the light and also their corresponding positions, just to make sure that, at any point in our detection process, are we going to have photons that are red and then occur much further than that of the blue photons? But at least with the two cases that I was looking at, specifically with electron and muon, that we actually just keep this corresponding fraction as we get further and further from the initial shrink-off ring. And there's no dependence to measuring any kind of green wavelength at any kind of further position than that of any of the other colors. Now, getting into the overall concept of what kind of detector design that we could use. So this kind of mission, especially since we would only be in the focus for a couple of years, we would not be a large scale mission. So if we piggybacked onto other missions that are going out to either Neptune or Uranus in these timeframes, can we have a small scale spacecraft similar to that of CubeSat, but still achieving this kind of 5 to 10 meter size detector, which a 5 to 10 meter size is actually much bigger than that of Hubble as well, because Hubble actually only has a mirror size of about 2 to 2.5 meter width. And so can we still have something that's small detector, but still achieving that high diameter? And then how can we tell these signals apart from events that occur in the atmosphere itself? And then looking into a concept of powering this kind of spacecraft that far from the sun. Now, the detection process that I was looking at, or in that me and Salome have discussed, is essentially having a multi-sensor system that has a UV sensor, infrared sensor, and then a few other ones looking at these either scintillation or fluorescence processes. Now, the IR sensor is to look at specifically for if there's lightning occurring in the atmosphere, it's going to create wavelengths in the entire spectrum, but very prominent signals in the infrared. So if we were to see something in that sensor, then we would say that, oh, this did not occur from a shrink-off event or a scintillation or a neutrino event in general. And then also be able to just distinguish between these neutrino events and any kind of the natural backgrounds that would occur in the atmosphere itself. And so essentially creating these kind of identification markers that we can use for future simulations and looking at specifically with shrink-off, scintillation, fluorescence, lightning, and auroras. For one, what kind of spectrum would we expect from each of them? The timings that each of those kind of processes could have. The direction, which shrink-off again is going to be that more forward cone, while the other ones are going to be isotropic in nature. And then looking into kind of a selection criteria of what we would want to consider as these kind of neutrino events and these rejections of either lightning or auroras that happen in the atmosphere as well. Now, getting into the size detector. So as I mentioned, have something that is probably on the order of a 3U CubeSat as the main housing for our electronics, our sensors, and any kind of way that we can power the system. But in order to achieve this kind of large light collection power, there's actually a concept being studied by JPL, which was looking at essentially encapsulating their satellites or spacecrafts in a bubble so they can still use solar as a form of power, especially when they are very far away from the sun. And so about half the overall bubble would be coated in a reflective layer. So for one, allows for a greater light collection that they would use typically for solar power, and then can also be used as a radio dish for communication. So meaning that we don't have to take something that is very large to still communicate while we are far from the sun. Now, looking at a kind of sketch of what this would be is that we would have this kind of 3U being at the center and with a reflective layer pointing towards the Earth. So, or pointing towards Neptune itself. So as these light rays come in, they're going to bounce off this reflective layer and be incident upon our CubeSat. And so we can still achieve that high light collection, but with minimal mass instead. And then if it's filled with a kind of greenhouse gas, we can have a greenhouse effect to keep similar to that of a temperature controlled environment, especially for electronics, which might have certain sensitivities to temperature as well. And then, so getting into power generation, I mentioned that that kind of bubble concept could be used when we are at further orbits, But when we start looking at what kind of solar irradiance that we measure out at Neptune or Uranus, so what we measure here at Earth is about 1100 watts per meter squared. And so CubeSats can definitely use a small area to power themselves as they're orbiting Earth. But when we get to Neptune, it's about 30 times the distance of Earth. And so we have actually a reduction of 1/900 because, as I mentioned earlier, the 1/r² dependence on the flux coming from the sun. And then also half of our orbit would be essentially in the planet's shadow. So using solar as a form of reliable power generation would not be a suitable way to do this. But we can also use this kind of concept of the magnetic field of the planet can be used with something called an electrodynamic tether. Now, an electrodynamic tether has been looked into for studies of either nanosats, CubeSats, or either large-scale spacecrafts. And so some of the studies that I found was that a 10-meter long tether can actually produce about 1 kilowatt of power, and that's a continuous power on average as it orbits Earth. And so if we start looking into what that fractional value is, it's about 0.1 watts per meter. And so that would not be something that is for a small scale tether to power our CubeSat when we are that far from the sun. But one thing to account for is if we just look at the magnetic field strength of Neptune versus that of Earth, it is 27 times greater. So we can take that same fraction as previously and see that we get about 2.7 watts per meter. And so something that is on the order of maybe 2 or 3 meters would actually be substantial to power a CubeSat. And especially if we are going to be powered down for about half the orbit when we're on the light side of the planet, we'd still be able to start charging our craft using this tether system. Now, there are some remarks that go along with it is that with induction into this tether, it'll also create an opposing force. And so it'll degrade the orbit over a period of time, which can be seen as a benefit and a downside, because that means that we'll have less time to orbit the planet, but that means that we can get closer and try to see these detections much closer to where they're occurring in the atmosphere. Now, as I said, there's lots of future work and refinements that we want to do with this project. And some of it is to look at this, the atmospheric studies, especially since a lot of these properties aren't known. So if we can obtain a gas mixture with the corresponding volume fractions, we can start going through and try to measure the scintillation properties, study the attenuation length and index of refraction to make sure that the values that we chose are in a reasonable ballpark for what we did for these initial simulations. And then what kind of contributions would we have to the from the auroras? What spectrum do they occur in? And then how frequently do they occur in Neptune's atmosphere? And then going through with the refinements to the simulation. So I had that determine the source of memory leak, which I actually just found last Wednesday. So I'm able to go through and perform additional simulations runs, especially as the semester finishes out and as we go into the summer. Focusing more on that close approach between at the surface and probably about 100 kilometers, but we also have to possibly partner with the aerospace department to try to find out what kind of reasonable orbits that we would want to go around either Neptune or Uranus. And then also wanting to implement this detection process into JAMP and be able to start looking at the different spectrums and then have this essentially rejection process to make sure that as we add lightning into our simulation, are we able to reject that confidently as well? And then start going into some of these neutrino studies of is there any kind of contributions for these neutrinos passing through the interior of the sun? And then the expected rates that we would have for the interactions occurring in the atmosphere as well. Now, one thing I want to mention with what kind of versatility this type of detector could have is looking into if we can map the interior of the ice giants, imaging various pulsars that also emit these highly energetic neutrinos, and then any kind of neutrino measurements that we want to look at while we are out at either Neptune or Uranus. Now, when we start looking at the interior of the ice giant, so on the figure on the right is what we currently believe is the inner structure of that of Neptune. So we have a rocky ice core, mantle that is a little bit of water and ice, and then getting out into the further atmosphere. But how can we use the same type of detection process to start doing that mapping? And as I mentioned before, so these muons that are going to be created in the atmosphere can travel much further than that of the electron case. But we also have those instances where it'll decay into that of electron, which then we can observe from a spacecraft that is orbiting, because we'll have a signal that appears in the very last portions of the atmosphere. And then we can also use this process or this effect that I mentioned earlier called the Askaryan effect, and which is this burst of radio waves that's created when these ultra high energy neutrinos interact with an ice media, or anything that is typically an optically transparent one, that this kind of cascade effect can happen of neutrinos of about 10 PeV and above can actually create. So while we are orbiting the planet, we can start looking for these kind of radio signals within the inner structure of the planet and try to find out, for one, where do they occur, their intensity, and then try to have an idea of going through and mapping out that the overall structure, either from the core or the mantle itself. Now, when we start looking at other sources of neutrinos, so this is an image from the Fermi Gamma Ray Telescope, which is looking at all these gamma ray sources, which the same process that create the gamma rays can also create these energetic neutrinos. So we can start looking at other spots that kind of align with our orbits or our gravitational lensing to find out, oh, what else can we start to look at or image within Neptune or Uranus. Now, what we were initially looking at was the galactic core, which is occurring about this crossing right here. But the white line that we can see right here with the dates is the Earth's relative position at different portions of the year. So if we look at where we cross the galactic core, or when we are aligned with it, we see that we're about December timeframe. And then if we look about half an orbit later, we see that we align with some of these other bright sources, which are two pulsars that we can start to figure out what kind of signals that they produce, and can we also use those same sources to try to image using either Neptune or Uranus as well. Now, that would be half an orbit later for us, so that should also be half an orbit later for Uranus and Neptune after we pass the galactic core. So 40 years later for that of Uranus, and then I think it's 70 years later for that of Neptune. And so we can start looking at those other sources when they've reached about half an orbit later from that galactic crossing. And then getting into at least some of the neutrino measurements that we can start doing is, if we're able to determine the flavors of these neutrinos, we can start to have an idea of the neutrino oscillations from where the sources are created at the galactic center, and then what kind of signals do we measure in these atmospheres. And then again, refinements to the upper limit of neutrino mass, if we can do that with these kind of neutrino detections, but also just the fact of looking at the Askaryan effect in planetary bodies, because we've only been doing that with the ice in the South Pole instead. But if we can see that in these other celestial bodies, that would be interesting to see. And if we can use that to then start mapping out the inner structure as well. Now, just to kind of conclude on everything, and especially we are hitting right at the 3 o'clock mark, is so the ice giants are natural and useful targets for these neutrino interactions. And so we don't have to take something that is very large out to them. We can use that natural media instead for these neutrinos coming from the galactic center. What was learned from the overall simulation so far? Very prominent signals for detectors that are very large, between the 5 and 10 meter mark. Timings are very prompt between both the processes, and that's partly the portion of scintillation still needs further studies to look at what the decay is, or what the scintillation decay is for that specific process. And then large fractions of the wavelengths occur in the UV and blue portion of the spectrum. And then what do we need for this type of detector? That detection and rejection scheme, implementing that into GEONT and seeing how confidently we can either accept or reject those signals. This kind of bubble environment to, so we don't have to take this kind of large scale detector out, but having this increased light collection power, this electrodynamic tether to be able to power our system, especially that far away from the planet. And then going into this continued work for refinement of the simulations, and then more studies into the versatility that this craft could be used for. And so that is where I'm going to end today, and I will accept any questions. I know some people have to run, so either put in the chat, you should be able to unmute yourself too, and then if you have any questions here in the room.
you're here in the room, he has the only mic that people want to hear.
Yes. So if you have a question in the room, I will bring the mic to you and then can answer that.
So I heard on NPR yesterday, I think it was yesterday when I was driving home, that the planetary divisions got together and determined their decadal survey. And they want to emphasize an orbiter around Uranus.
I know.
But I don't know, they don't have a time frame.
Yeah.
It's just they want to do it.
Right.
So what do you think?
So I know Salome actually mentioned this this past Friday, that the Uranus mission that I know Neptune was planning was actually scrapped overall. So that one's not actually going to be something that is going to be done in the future, at least right now, because of budget constraints. But the Neptune one, there is one that is being planned, but that same kind of budget made it so this kind of craft that is going to be going out to Neptune at least is going to be shifted by at least 5 years. So they can go through and budget everything. But I know both of them are not going to be funded. It's going to be one or the other. And it looks like they've decided to not go with the Uranus mission, but that still gives us time to look more at the Neptune crossing as well.
You have a big comment there in the chat.
Nest points the last time to launch to Neptune is 2055, and after that, no launch window until 100 years later because the fuel and cost goes up and due to the gravity assist. This one is the nicest and intriguing new ideas they've seen in years. Yeah, I was just making sure that there was no underlying ones that was hiding in there. So as Salome mentioned in the chat, so President's budget ruled out Uranus in favor of Neptune, but decadal survey this morning did the opposite, I am told by NASA people here. Oh, okay, so it might be now opposite of that.
Well, the decadal survey is done by the experts and by people at NASA and you know the actual scientists, not the budgetary or political people.
Right.
So the political people are the one that actually control the purse strings and
Always.
and yeah, it's politics that happen. Wait,
right. Any other questions here in the room at all? Yeah, I know I at least had to rush through a few points, but just to make sure that we weren't going over too much in time. Thank you. And any other questions in the Zoom land at all? You can either unmute yourself or put in the comments.
So while you're thinking about questions, let me remind everybody next week on the 27th, we'll have another seminar from Anthony A. Folder of CERN, who's going to talk about one of the upgrades to Atlas and at the LHC. And then the week after that will be Professor Lewis from University of Kansas on a topic to be determined.
So Salome just asked one more question.
Yep.
So will we hear more about this later? So that's something we actually found out about last night, is that a few of us on the New Soul project, but also for this same discussion to give a presentation in Paris this September. And so that'll be discussing more of the research that I presented here, but more in a confined detail, and especially with some of the updated results that I'm planning to do for the summer as well. But it'll be at least nice to present that at a conference, and for some of the new things that we're either wanting to study that we found, and then where we can go with this overall kind of concept. Oh, I know, so bad. I'm excited because I still haven't yet to leave the US at all. I already did, and surprisingly, it came in 3 weeks. Yeah, I didn't even pay for Expedited. But if no one else has any questions, then we'll probably end here. And then if you have any questions, either you can message Dr. Salome or even myself.
Thank you very much.
Thank you, everyone. Definitely a few points I was like, where am I at again?
Thank you.
I don't know if we want to end.